Okay, so hello, and today we're going to be looking at the inter-rater reliability of dimensional data, ratings that are made on some kind of a continuum or rating scale, as opposed to qualitative judgments made as to whether someone belongs to a given category or not. As usual, we're going to go into slideshow mode, walk through some of the basic concepts, the equations, and some examples as we go. So without further ado, here we go. Now into our little how-to guide. And all right, so first off, what do I mean by dimensional judgments? Essentially, this means that we're operating in an interval or a ratio scale, the kind of scale where the numbers actually act more or less like numbers, and we can engage in conventional statistical operations. What this means is that the ratings we assign are quantitatively different from one another. If you get a score of 72 and I get a score of 68, your score is higher than mine. And in fact, if we're on an interval or a ratio scale, your score is just as much higher than mine as a 76 is higher than yours, that the numbers are actually equivalent in terms of the quantity that they represent. This is all over the place in psychology, education, and the sciences generally. If we're asking, how intelligent are you? Whether we're talking about an IQ test or some other form of intelligence, when we ask, how much is your back hurting after sitting at that computer all day? When we're asking, so how hot's your bod? When we're asking, hey, what's your mile pace? How fast do you run a mile? These are all continua, right? In every case, we could say that anyone we could possibly be studying has at least some of this characteristic. We all have some intelligence. Our backs have all hurt a little bit at some point or other. We all got some hotness, and we can all run or at least move from one place to another. The question is not, is it there at all, but how much of it is there? Okay, so we want to establish the reliability of these judgments in cases where there is judgment involved. And so in doing so, we're dealing with what are really scores. And the good news here for those of us who are students of psychometrics is that everything we're doing is pretty familiar territory. We're going to be dealing with correlations and reliability coefficients just as we do when we're studying or deriving values for internal consistency or test-retest reliability or parallel forms reliability. Now, when we're in this inter-rater mode, there are two main methods out there for calculating and reporting reliability. The first of these, and the older, is the good old Spearman-Brown Prophecy Formula. You first saw this, I suspect, when you were studying split half reliability, but this is just another variation on the same equation, which has now been kicking around for over a century and is still doing pretty good service for us. Also pretty easy to get this one by hand. As long as you have some way of generating those correlation coefficients, you just have to plug in the basic equation. As we'll see, it's not that complicated, and you're there. The other approach is what's known as the Intraclass Correlation Coefficient, or ICC. This one may be a tad more sophisticated. We'll see how in a little while. Though generally speaking, the results you get from the two procedures are almost identical. So it doesn't really make that much of a difference which one you use. The ICC is, however, a bit more cumbersome to come up with by hand. So if you're operating in a statistics package such as SPSS, usually there's a little unit in it where you can just call down the menu or type in a little code and the ICC will be spit out for you. But if you aren't in that kind of environment, just go with the Spearman-Brown formula and you should be fine. Again, they're really almost interchangeable, really. And you should know about both because you'll see both reported in papers that you're reading. So the Spearman-Brown formula. There it is. It should be recognizably well, recognizable as a variant on what you've seen before. We're trying to solve, in this case, for big R. Big R is, or capital R, is the reliability of the pooled ratings of all the judges, all the raters we have available. So if I have 3 judges, it's all 3 of them. You could be adding them together and just doing it that way. You could be taking an average of the 3 or a mean of the 3. It doesn't matter. Same deal. That's what we're solving for. The 2 things we need in order to get there are, first, the number of judges or raters, terms I use interchangeably, judge and rater, and the mean correlation across judges. That's this little R bar thing. You know, the little italicized R is always the good old Pearson product moment correlation coefficient, Pearson's R. The little bar over the top means that it's a mean or an average. Now, there is a little side thing I should mention here. There's some controversy about how best to get that mean. I'll come back to that in a minute, but you're not going to have to worry about it a whole lot. But that's it. Just need to know those 2 things. So how does it work out? Well, the first thing, or how do you work it out, rather? The first thing you need to do is to, of course, obtain the correlations across the different judges or raters. Again, if you're a student in my class, I will provide you with those statistics. You won't have to get them for yourself. But they're pretty easily derived, even in a spreadsheet environment these days. Then you're going to take the mean of those correlations. Now, I did say there's a little controversy. Let me just address that. Strictly speaking, this is very technical stuff, and I apologize, but you don't have to worry about it too much. Strictly speaking, the distribution of values of correlation coefficients violates one of the assumptions of the general linear model. You know, I know, shoot me now, right? And so some, all the way back to Spearman's day, in fact, he started this, have argued that you ought not to use them as data points, that you can't like add them up and take an average without first converting them into this other statistic known as Spearman's Z or R prime. Then you do all your little math over there, and then you convert the result back to good old Pearson's R. Nowadays, there are many authorities who say that this is not necessary. And in fact, when I've looked at it, you know, empirically and just like run some data sets out of curiosity, the results are almost always like virtually the same. Like the mean correlation might change from 0.43 to 0.42, you know, but that's about it. So I don't make people do this. And in fact, you can find, you know, reputable authorities who actually know this stuff way better than I do, who will have written that you don't need to do it anymore. But if you ever get called out by, you know, the crazy reviewer number 2 on your paper, there are still those who say you should do it. So let's try to forget about Spearman's Z immediately. We're just going to take the mean of the correlations the old-fashioned way, add them up, and divide by how many you had. Now, importantly, that R bar value, that mean correlation, it's a reliability statistic in its own right, because that's actually the reliability of the average individual judge. Now, for some purposes, that's actually the more important statistic. If, let's say, you're developing a clinical test and you're studying the reliability of your clinical test, which requires judgment to be scored, well, in practice, it's usually going to be just one clinician rating test protocols. You know, when I conduct a diagnostic interview or run a Rorschach inkblot test by somebody, I don't usually sit down with 3 other psychologists and, you know, we all like go through the transcript independently and write our own little answers down and then compare notes. Instead, what, you know, usually happens is the one who interviews you makes the rating. The one who Rorschached you is scoring the Rorschach. So in actual clinical practice, that R bar value is telling you how reliable the judgments are going to be. However, in a research context where we have the luxury of having 2, 3, 4, or more judges look at the same protocols, we can smoosh them all together and gain enhanced reliability out of that. Just as Adding items to a scale is likely to make the scale more reliable. Adding judges to a pool of judges is likely to make the collective judgments more reliable. So we've got the mean correlation. Now, the numerator of the equation is simply the number of judges times that mean value. That's the numerator. To get the denominator, we're first going to multiply that mean correlation times one less than the number of judges, one fewer judge is than one has, and then add 1 to that value. That's the denominator. So the numerator is just n times r bar. The denominator is 1 plus n minus 1 times r bar. So then you just divide the numerator by the denominator, and you've got it. Now we're going to walk through an example, of course, because that's a lot to take in without any actual numbers in front of you. So here we go. We have our old friends, Dr. Schnitzel and Dr. Martinez, who are still looking at human figure drawings and trying to identify psychosis using these test protocols. And in this scenario, they are using a 10-point scale to rate how bizarre the human figure drawings are, like the degree of bizarreness, ranging presumably from like a 1, meaning this is a really standard issue, staid, boring, nothing odd about it, up to a 10, which would be something extraordinarily bizarre. So they've done this to a number of human figure drawings, and they calculate what the results show. So Dr. Schnitzel, Dr. Martinez, note this, I did provide you here with the means and standard deviations for each judge. Most research reports would do the same, but you don't actually need that in order to get the reliability coefficient. So it's actually extraneous data. We might note in passing that Dr. Martinez seems to think the average drawing is a little more bizarre than does Dr. Schnitzel, but we don't know what to make of that. And right now, it's not our concern. What is of concern to us is that their ratings correlate at r equals 0.48. Now, we have only 2 judges here. So with only 2 judges, we don't need to take a mean of the correlations. There's only one correlation. So r bar is simply r. So the numerator is simply 2, the number of judges, Schnitzel and Martinez, times 0.48. 2 times 48 is 96. So we have 0.96 in the numerator. The denominator is 1, that just sort of constant 1, added to, in parentheses, 2 minus 1 times 0.48. Now remember your order of operations. We do what's in the parentheses first. So that 2 minus 1 becomes 1, which is then multiplied by 0.48, which of course just gives you 0.48, and we add that constant 1 in to get 1.48. So again, 2 minus 1 is 1, times 0.48 is just 0.48, and we're always adding the 1. So big R is 0.96 divided by 1.48, which comes out to about 0.65. Notice, as always, reliability coefficients will range between 0 and 1. And also, when you're doing these inter-rater reliability exercises with the Spearman-Brown formula, and you add judges, it'll always go up. So an individual, Martinez or Schnitzel, we might say would only have reliability of 0.48, which by the way is pretty bad. But combined, we've reached a reliability of 0.65. Just as an aside, as you may recall, a reliability coefficient in the mid-60s is probably okay if we're conducting research using samples of people where you've got 30, 40, 50 or more people in the sample, but it's probably not good enough for routine clinical purposes. It's way too much error still built in there. Now, yes, order of operations. Now, let's look at a 3-judge case. We'll also do a 4-judge and then kind of bail on the examples. So let's use a different example. We're looking at applicants to a congressional internship program. And it's a high prestige program, lots of people apply, and it's also considered to be high stakes enough that they want to get good people in the positions. So they have 3 experienced congressional aides rate all of these internship applications on some kind of 100-point scale, kind of like grading them, basically. And here's how the ratings correlate. I didn't make up names for the aides, so we're just going to call them aid 1, aid 2, and aid 3. And so aids 1 and 2 correlate at 0.42, 1 and 3 at 0.58, and 2 and 3 at 0.35. So again, we have 3 judges. Each judge's ratings can be correlated with those made by the other 2 judges, yielding a total of 3 possible correlations. I'm not going to bother you with the descriptive statistics here. If they were present, again, they wouldn't factor into the reliability calculations. So what's our solution? Well, the mean correlation is, drum roll, please, we add up the 3 individual correlations, 4, 2, 5, 8, 3, 5, and we divide the sum by 3, which gives us a mean of exactly 0.45. So the numerator of our equation is 3 judges times 0.45, 1.35. The denominator of the equation is 1 plus, in parentheses, 3 minus 1 times 0.45. So again, in parentheses first, 3 minus 1 gives us 2. Then we multiply. 2 times 0.45 gives us 0.90. Then we add the 1 in and we get 1.9. So the numerator, 1.35, the denominator, 1.9. So R is 1.35 divided by 1.9, or about 0.71. Again, notice that by adding judges, we've boosted the reliability of the judgments from a state in which more than half of what we were getting was random to a state in which we can say, yeah, that's not too bad. Important little note for those of us who are prone to making little slips along the way. The 3-judge scenario, when you have exactly 3 raters, that's the only case where the number of raters and the number of correlations between the raters is going to be the same. So you can actually, don't have to worry about it, but with any other number of judges, you have to be very careful not to get those 2 things confused. The mean correlation is the mean across the number of correlations, whereas what you have in the Spearman-Brown formula is the number of judges. So we'll do a quick 4-judge case. Here we'll make it a business case just for variety's sake. So we have 4 partners in a private equity firm, and they get lots of investment proposals. Lots of people are saying, hey, put your money in my great idea. And so they decide to assess how reliable their ratings are. They use a 20-point scale in making ratings of investment proposals. And so here are the results. I did give them names because I figured, why not? So we have Messrs. Hassan, Smith, Jacobs, and O'Grady. And here's the correlation matrix. So Hassan's ratings correlate with Smith's at 0.46, with Jacobs's at 0.52, with O'Grady's at 0.63, and so forth. Note that with 4 judges, we now have 6 correlations. I'm not giving you all the descriptives on it, so I'm not telling you whether Hassan or O'Grady is an easier or a tougher judge. Besides, it's a made-up example, so it wouldn't help you. Okay, the solution. Well, the mean correlation across raters is, add up all of the 6 individual correlations, divide by 6, which works out to just about 0.51. If you wanted to say 0.507 that would be fine too. Okay, so the numerator is 4 judges times 0.51, or 2.04. The denominator is, here we go again, right? 1 plus, in parentheses, 4 minus 1 times 0.51. So first we do the 4 minus 1 in parentheses to get 3. Then we multiply the 3 times the 0.51 to get 1.53. Then we add the 1 to get 2.53. And the answer is, R is 2.04 divided by 2.53, or just about 0.81. There it is. Again, remember to keep these two concepts distinct. The number of judges and the number of correlations are not the same unless you have exactly 3. So how many judges do I need? Let's think of a very practical question here. You're probably getting used to my saying this on some of these presentations, but it depends. There isn't a mathematical answer to this. It depends on two things, really. One of which is how strongly the judges correlate with one another. The other is how reliable we need the ratings to be. Like how urgent is it that we achieve a given level of reliability here? So let's just look at what happens when you increase the number of judges. We won't speak just now to whether they agree more or less strongly, but just assume that we have judges correlating on average at 0.4, which is a moderate correlation, but not a strong one. Well, if we have two raters, the reliability of the two combined is 0.57. Nice jump up there from 0.4. With 3 raters, and this is just, you could check these numbers for yourself and see if I made a mistake, but I just plugged in the Spearman-Brown formula, basically. With 3 judges, we're up to 0.67. So we've made another nice little jump up. With 4 judges, we're up to 0.73. We're still gaining. You will always gain, by the way, but you will notice that it's tapering off a bit, isn't it? We're not making as big an increase anymore. We went from 40 to 57, that's a 17 jump. Then we had a 10-point jump. Now it's only a 6-point jump. You go to 5 raters, and we're gaining another 4, 0.77. So it's starting to get expensive, isn't it? As you get past about 3 or so raters, to get a lot more reliability, to squeeze a lot more reliability out of a given level of agreement is going to start getting expensive. You're going to have to use a lot of raters. If, for example, if we bumped it up to 10, we could actually have that reliability statistic all the way up to 0.87. Now, would you ever actually do that? Yeah. If you have something that's very difficult to rate reliably, where you really can't get precise measurements from individuals, but it's important to you to know the truth, then yeah, having 10 or even 12 or 15 or 20 judges might be the only way to get there. Oh yeah, 20, we'd actually be up to 0.93. That's how much of a difference it can make. But again, getting 20 people to look at all of your stuff is not going to be easy. Now, briefly, we will also look at the ICC, the Intraclass Correlation Coefficient. And again, I'm not going to require you to calculate this by hand, although I'll show you an example in a minute of how it can be done. It's an important alternative to the Spearman-Brown. Generally, again, not going to give you a very different result. The one difference that makes the ICC arguably a little more sophisticated is that it is sensitive to systematic differences across judges. So if you have one judge who tends to give you much higher or much lower ratings than the others, that's going to exert a little bit of a downward pressure on the ICC. It doesn't affect the correlations at all. So the Spearman-Brown formula won't pick up on it. The ICC will, but usually unless the differences in their mean scores are huge, it's usually not going to be much of a difference. Hand calculating it, it's doable. If you only have 2 judges, it's not that much of a pain in the neck. But if you have like 4 judges, you just don't want to do this. It's tedious. Just do the Spearman-Brown and get out of there. But again, statistical software packages like SPSS tend to have it built in. So I'm going to look at with you at an example. In fact, I'll stop the share for just a moment and instead share into our little data set here, and then we'll just conclude and wrap up. So what you're looking at now is a spreadsheet that contains data on some ratings that were made actually these were of sentence completion protocols. So the participants in the study had each completed 40 sentence stems. The 2 raters had been trained to evaluate each stem, or each completion rather, each sentence, in terms of whether it reflected a high or low level of the trait known as neuroticism, or was just neutral. So they could have a 3-point rating, -1, 0, +1 for each. What I've done here is to arbitrarily add 10 points to their final scores so you wouldn't get negative numbers, but that doesn't change anything. So we have 1 rater here. These are all of his ratings for the cases, and there were, I think, 75 cases, or is it? No, 74 cases. And then here we have the second rater's scores, and she too rated the same cases. Now, if we look at the bottom here, these are the mean scores for each of the 2 judges. And you'll see that they do differ a bit, don't they? So one has a mean score of 11.84, the other at 17.51. The standard deviations are around 4, 5, 6. So they're about a standard deviation apart. They are giving you, on average, somewhat different ratings. However, their ratings correlate. That's the number I'm highlighting now. Their ratings correlate at 0.64. So they're actually agreeing pretty well as to what they're seeing. And if we combine their 2 judgments and plug in the Spearman-Brown Prophecy Formula, which is actually visible in the formula bar up here, we find that the reliability of their pooled judgments is 0.78, which is actually rather good. So that's how you do the Spearman-Brown. Again, you can just literally plug it in with 2 judges. It is the same as the split half formula, by the way. So how do I get the ICC if I want to do this by hand? And truth is, I don't. I only did this for you, and you'll probably never want to do it either. But what you do is create 2 new variables. One of them is created by combining the 2 scores you had in one order. So you see rater KN assigned an 8, rater PB assigned a 24. So it becomes 8, 2, 4. The other one, the other way around. So it's 24 followed by 8. And that's it. 5, 15, 1, 5, 5, 13, 14, 14, 13. So for each case, you're putting down the 2 scores just kind of smushed together. I know it sounds a little weird, but there is some fancy underlying mathematical reasoning as to why this is a great idea, and I didn't invent it. So when you've got all of that done, by the way, I hope you see why you don't want to do this. You literally, I don't know of a way to make a spreadsheet do this. So you're literally going like 1, 1, 1, 7, 1, 7, 1, 1, and it's just, and that's just for 2 judges for only 74 cases. When you've done it, you can simply correlate those 2 columns, and lo and behold, you've got the intraclass correlation coefficient. Do notice, again, the 2 means were different by a standard deviation, but the ICC and the result of the Spearman-Brown procedure are literally only off by 0.01. They're essentially giving you the same result. So again, in practice, it's not really going to make much of a difference which procedure you use. Do whichever one comes easier. And that said, we'll just wrap up with our little slideshow, conclusions, and get out of here. So, bottom line, whenever you are scoring some piece of work, something you're evaluating, whether that's somebody's term paper being given a grade, it's a film review with a number of stars, a rating of an investment quality or a bond rating by Moody's Investment Services, or the score given by a National Institute of Health panel to a scientific grant proposal. The objectivity of the score can be called into question and should be evaluated. All too often it is not in practice, but it should be. The iterator reliability statistics we've just covered are exactly the way to do it. Surprising how few people seem to know about these out there. It's a skill set you now have and you share with only a relatively small proportion of the population. Really, you can use either the Spearman-Brown Prophecy Formula or the Intraclass Correlation Coefficient. The latter may be a little more sophisticated, a little more conservative, but usually it's not really going to matter which one you use. And that concludes our presentation. Go forth, if you're in a assessment class, do some practice exercises, get yourself comfortable with this, and you should be good to go.